For my thesis defense today, I will be talking about the control of jump stochastic systems by learning recurrent spatiotemporal patterns. So the motivation of my work is as follows. I find that current methods for model-based stochastic control works for a rather limited scope of stochastic disturbances. One such example being Gaussian white noise. So here's an example of white noise with positive drift. It's nice that this room has this little stick thing, so I'll be using it a lot. So here's an example of white noise with positive drift. You can see the upwards slope here. And Gaussian white noise systems are appealing to study in both theory and application. So on the theory side, Gaussian distributions demonstrate convenient properties such as the central limit theorem and Gaussian, the linear combination of Gaussian random variables are themselves Gaussian distributed. On the application side, Gaussian white noise systems have a lot of real-world systems for which the model works well. For example, localization and mapping, as well as spacecraft navigation, etc. So as a result, many algorithms for controlling or estimating Gaussian white noise systems have been developed in the literature, such as the well-known LQG control and Kalman filtering. So what about stochastic systems that fall outside of this model class? For example, if we have white noise, but it's also perturbed by shot noise, which is responsible for these red impulsive jumps, well, then control and estimation is typically left for model-free techniques in artificial intelligence. And fortunately, increasing capabilities in big data analysis have made it possible to rely almost entirely on end-to-end AI for controlling these complex stochastic systems. Still, training AI methods can often be exhaustive in computation time and energy, especially if they redundantly learn data that could be obtained from structured models. So if we go back to the example from before, this shot noise process, which is responsible for these impulsive jumps, can be modeled with compound Poisson processes. And compound Poisson processes have a lot of theory and tools that are developed for it in the applied math literature. So the title of my thesis today mentions something called jump stochastic systems, which I define to mean systems with random and repetitive jumps. I chose to study jump stochastic systems in my research because they are also appealing to study in both theory and application, similar to the motivation of Gaussian white noise that I described in the previous slide. So there are many applications of jump stochastic systems in the real world. For example, agile quad-order flight, spacecraft control, robot manipulator, power grid, rain signal imaging, vehicle traffic congestion, and epidemic spread. As a minor disclaimer, I borrowed a couple of these figures from other papers in our field. So some of you might recognize them. Jump stochastic systems can be partitioned into several classes. So on the left side of the slide, we have fault-tolerant systems, where the jumps are the faults or external disturbances of the system. So in the case of agile quad-order flight, these sudden gusts of wind perturbing the quad-order could be thought of as jumps. In spacecraft control, meteorite strikes to the system can be thought of as jumps. In robot manipulation, obstacle collisions, like this person's hand hitting the robot, can be thought of as jumps. And in power grid, line failures due to extreme weather conditions, which cause changes in the topological structure of the grid, can also be thought of as jumps. Let me admit this person to the Zoom meeting. Okay, on the left side of the slide, we have event-driven systems where the jumps are an inherent part of the dynamics. So in brain signal imaging, the neuron spikes, or the neuronal spikes, can be thought of as jumps. In vehicle traffic congestion, the vehicle arrival processes are a type of jump process. In epidemic spread, as we've seen with the recent COVID-19 pandemic, the emergence of variant viruses, such as Omicron and Delta variants, can be thought of as a type of jump. And super spreader effects can also be thought of as a type of jump event. We also have network applications where spatial and temporal repetition arise in the jumps of the system. So for example, in vehicle traffic congestion, there's spatial repetition due to the structure of the grid topology, and there's also temporal repetition due to human routine. This can also be extended to biological networks, such as epidemic spread, and the brain signal imaging can be extended to neuronal networks, where those neurons might fire across various regions due to the structural connectivity of the brain. In my thesis today, we're going to focus exclusively on discrete time and discrete event jump stochastic systems with repeating jump patterns. And one specific architecture that we'll design is based on something we'll call pattern learning for prediction, or PLP. PLP achieves efficient control by learning patterns in the system behavior. And this occurs in two ways. So we can either memorize past patterns, so we can prevent the recomputation of repeating control policies, or we can predict future patterns so that we can schedule control policies in advance. We'll also be looking at two examples in the real world: dynamic topology networks like the power grid, where the patterns are sequences of line failures and consequently topology changes, and the vehicle traffic network, where the patterns are intersection snapshot sequences over time. Okay, so before we get into the meat of this of my thesis, I want to allude to some related work. So the broad aim of my thesis is that we want to expand the capabilities of model-based control design so that we can use model-free techniques as a supplement instead of implementing them end-to-end. There have been many papers that work towards the same broad aim, such as robust and adaptive control of uncertain systems, meta-learning-based algorithms, and storing past information while learning, as well as predictions for structured control. And many of the proposed controller architectures in this literature follow one of the four types of architectures on the right side of the slide. So in the top row, suppose we're given partially known system dynamics. We can learn the uncertainties of the system and then design some kind of model-based control policy based on what we've learned. Or we can learn the uncertainties using AI, then develop a function representation of what we learned, and then implement a model-based control policy based on this kind of model functional representation. On the bottom row, suppose we're learning unknown system dynamics. We can either learn the unknown system dynamics as a whole, then develop a functional representation of that, and then implement a model-based control policy for that. Or we can learn the control policy itself and then design a functional representation of the control policy. Okay, so in order to demonstrate concretely this concept of pattern learning for prediction, I will use this specific form of the uncertain discrete time linear Markovian jump systems, which has this following linear dynamics. So here we'll note that the A matrix takes as input this argument psi sub n of t, which is the so-called mode of the system. This mode is a mode process which switches according to a finite state Markov chain with state space x calligraphic and transition probability matrix given by P. We're going to be distinguishing the random variable of the mode psi sub n from the real value that it takes. So this is similar to the probability notation. Typically we have, like back in probability class, capital X would be the random variable and little x would be the real value that it takes. So we can write expressions such as probability of big X is equal to little x, and so on. This W of t term is the external disturbance, whose distribution we'll assume is unknown. But for simplicity, we'll assume that its infinity norm bound W bar is known or otherwise attainable from techniques in robust control. So this subscript, big N of t for this mode, is the number of jumps or mode switches which have occurred by time t. And t sub n is the time of the nth mode switch. For simplicity, we'll assume that the mode process is delta t times slower than the system dynamics. So if n of t is equal to little n, then n of t plus a delta t is equal to little n plus a for any natural number a. This is demonstrated in the figure in the top left, where the system dynamics x of t has a much higher rate of variability compared to the real value of the mode process, phi sub n of t. To distinguish the system's time index t from the mode index n, we're going to refer to this subscript n as the mode index of the mode process. We'll also make the following assumptions. The realizations phi sub n of the random variable mode process are unknown. This X calligraphic set, the initial mode psi sub 0, and the matrices A1 through AM as well as B are assumed known. The sparsity pattern of the transition probability matrix P are known, but its non-zero entry values are unknown. Okay, so here is the controller architecture based on PLP that we'll design specifically for the Markovian jump system we showed in the previous slide. It's composed of 3 parts highlighted in purple, and we'll go through each part individually. First, mode process identification, or mode process ID, is responsible for learning the unknown statistics of the mode process. In the context of the Markovian jump system from the previous slide, this means the hat phi sub n to the t variable and hat p to the t, so the current mode and the transition probability matrix. Now, these hats and superscript t's are here to emphasize that we're taking estimates of everything. They're time-varying estimates of everything. Okay. Pattern learning for prediction, PLP, is responsible for recognizing previously occurred patterns in the mode process. And here we informally define a pattern to mean a single mode or a mode sequence which is interesting to the user. So, for example, in fault-tolerant control, that could mean let's say that there is a sequence of modes that represents a specific fault, then that is interesting to the user and so should be kept track of as a pattern. Control law design is responsible for designing the control policy for a pattern when it is first observed. Its implementation varies by application, as does the PLP component and the mode process ID component. So we'll be going over these 3 in much more detail when we discuss the 2 applications that I mentioned earlier. First, I want to go more into detail about the PLP component. So let's define a pattern more mathematically. A collection of patterns, big psi, is composed of these psi1 through psi k variables, where k is the number of patterns, and each psi sub k is a sequence of modes. So you'll note that the psi kj is taking value from this X calligraphic set, the set of modes, and it's a pattern with constant length L. I do want to emphasize that the theory used for PLP can be extended to patterns with varying lengths, not necessarily constant length L for each pattern in the pattern collection. But because there's some implications with how these patterns are going to be used for prediction, this L is kind of like a horizon over which we're going to be predicting. And so it's convenient to fix the constant length to be L. Okay, so every sequence of modes or a pattern is said to be feasible if it can be generated by the mode process. That means that every consecutive pair of transitions in this mode sequence has to have a positive probability of occurring. We'll also define the pattern occurrence times for each pattern psi k in the pattern collection. So let n, which is again equal to big N of t, be the current mode index at the current system time t, and suppose that our current estimate of the mode is hat phi sub n to the t. Then the pattern occurrence times for each k in bit 1 through k is given by this hat tau k given n to the t quantity, which basically just says what is the number of mode indices after mode index n until we observe pattern psi k, given that the current mode is hat phi sub n to the t. The pattern occurrence problem is what's being solved by this PLP component, and this just basically extends the pattern occurrence time to the entire collection big psi. So given big psi, for each time t and n, we derive these estimates, expected value of hat tau n to the t, which is the mean minimum occurrence time to observe any one of the patterns in this pattern collection, given these conditions. And hat qk to the t are the first occurrence probabilities, or the probability that pattern k is the first to occur among all patterns in this pattern collection at mode index hat tau n to the t. Okay, so that was a lot of math notation, but hopefully this example will clear it up. So let's say that we have a collection of 3 patterns, psi 1, psi 2, psi 3. So the number of patterns k is equal to 3. Let's say that each pattern is length L is equal to 3, and that's 2, 1, 3, 4, 1, 2, and 3, 1, 4. And suppose that the mode process is generated from this Markov chain here. And I want to emphasize that these P1 through P7 transition probabilities, the true values are unknown, but we have an estimate of their values from the mode process ID component, which we use to design our current pattern collection. So let's say that the estimate of the mode process looks kind of like this. On the row of circles at the top, we have the mode process on the time scale of the system dynamics. That means 2 is repeated delta t times, 4 is repeated delta t times, 1 is repeated delta t times, and so on. The row of boxes in the center is the same mode process, but on the time scale of the mode index. And in red, highlighting 2, that's the current estimated mode at mode index n. Now it turns out that the pattern occurrence problem tells us that pattern 3, corresponding to 314, is the most likely to occur after hat tau n to the t mode indices from n. Okay, so how do we actually solve these pattern occurrence quantities in the orange box? So one approach is via martingale theory from mathematics, which have been studied in the literature, some referenced in blue. However, these works don't deal with learning-based control applications, and so they use assumptions which don't hold in the real world necessarily. For example, the mode process being known and the transition probability matrix and its other statistics are assumed known. So for the sake of time, we're not going to go over our version of the martingale-based approach to solving these pattern occurrence problems for our assumptions. But just know that they yield closed form expressions to these 2 quantities in the orange box. Okay, so let's extend our previous example to demonstrate what the overall architecture looks like, especially the control law design and PLP components. First, let G be a function which represents the mode-dependent control policy computed via control law design, which again, its implementation varies by application, and so we'll go into much more detail when we talk about the applications. We have our collection of 3 patterns again, and we again have that 314 is the most likely to occur at time, at mode index hat Tn to the T. Then what we do is we generate a sequence of controls for the entire estimated next pattern. So there's a G of 3 for this 3, and a G of 1 for this 1, and a G of 4 for this 4. We then schedule to apply the control law for just the first of all of these 3 scheduled policies, and this is similar in principle to model predictive control. The key difference between standard model predictive control techniques and what we're doing here is that we repeat the process over again at the next delta t time interval. And that's because of the nature of the Markovian jump system that we're dealing with. Okay, so let's now look at a couple of applications to demonstrate efficient control by learning patterns. Here's a slide that we've seen before, and we'll begin with the dynamic topology network application. So our network here switches among capital M different topologies over time, possibly according to an underlying Markov chain. And the dynamics are given by this linear Markovian jump system here. And n caligraphics of I of M represents the set of neighboring nodes of node I under topology M. So let's look at how the system fits within this PLP controller architecture. So first, the mode, as I mentioned before, corresponds to the topology of the system, and the mode process, psi sub n, is the sequence of indices of the topology. So for example, in this 7-node, 8-mode hexagon system, if psi sub n of t is equal to 2, that means that the system is currently in topology 2. And the plant dynamics here is just substituted in with this linear Markovian jump system dynamics that I discussed before. Mode process ID is implemented with something we'll call consistent set narrowing approach, which we'll describe later. And in this application, the patterns refer to the sequences of line failures, or correspondingly, the sequence of recurrent topologies over time so that we can recycle control laws. And finally, control law design is implementing disturbance rejection via the novel system-level synthesis framework, which we'll also go into detail later. So first, let's talk about the mode process ID component. So the general goal of mode process ID is that we use these state and control trajectories to estimate hat p to the t, which is the estimate of the true transition probability matrix P, and hat phi sub n to the t, which is the estimate of the true current mode phi sub n. Now, because the mode process abides by a Markov chain, we can use standard hidden Markov model techniques such as Metropolis-Hastings, Gibbs sampling, Baum-Welch, or Viterbi's algorithm to estimate these two quantities. Here, because we assumed that the distribution of the WT was unknown aside from its infinity norm bound, we're going to use consistent set narrowing, which is based on Ho and Doyle, 2019, and was also used in my paper, 2020. What we do here is we essentially take the system dynamics, isolate the W of t term by moving all of the other terms to the left-hand side so we get this kind of expression, and then we substitute this into the infinity norm bound that was imposed originally on this WT term. Then we check the number of modes in the entire set of modes, or sorry, the previous consistent set, such that it satisfies this inequality. So over here in this diagram, we have the evolution of the consistent set C calligraphic of T. Now in this third bubble here, let's say that the state and control observations, or trajectories, says that 2, 3, 5 are the modes that are consistent with those trajectories. Then it keeps narrowing it down by accumulating more and more data until it finally reaches to a singleton set. It keeps repeating this over every single delta t interval in time. Our update of the true mode isn't made until the consistent set narrowing approach narrows down to a singleton set. So now let's look at control law design. So system level synthesis is a method for distributed disturbance rejection in linear discrete time network systems with static topologies. So you'll note that compared to the previous slide, the dynamics at the top here no longer have the A matrices taking in as argument psi sub n of t, the mode. And that's because we're looking at static topologies. So typically a state feedback controller is used to control the system, and you can see this familiar block diagram here. In terms of the Z transform, the closed loop system is written in the following way. However, solving for the optimal K using this transfer function is difficult, especially when A and B are large scale. So instead of designing just the open loop feedback gain K, SLS, which was developed by the Doyle lab, designs for the entire closed loop system response through these response maps phi x and phi u. So basically it is a reparameterization of the standard state feedback law. One of the main advantages of SLS is its localized and distributed implementation over large-scale networks. And so it's common to design a local phi over each subsystem of the entire network system. So that's why I've included the superscripts I for every I in the set of vertices. I also have some work that extends SLS to dynamic topologies. So basically we try to design a single phi x and phi u response which can simultaneously stabilize over multiple topologies, or A matrices. So the closed loop response maps that we've seen before now have these additional sub and superscripts, T and M, M for the mode and T to indicate that it's time varying, and conditions for simultaneous stabilization over multiple plants in discrete time LTI systems have been studied for quite a bit in the literature. Okay, so here are the 3 architectures that we'll use for comparing our simulation results. First, we have the baseline, which is implemented without PLP. So, and control law design is implemented with standard SLS. So on the top right figure is we indicate what baseline does. So essentially, we use the control law for the previous time steps, the previous estimated mode until the consistent set narrowing approach narrows down to a singleton set. So for example, if at the beginning of this delta t interval, C of t is 1, 2, 3, then we've accumulated enough state and control trajectories to determine that 2 is the true mode. Then it keeps using the previous law until it finds that it's actually 2. Then it uses the response for 2, and then it just repeats that for the following time intervals. Topology robust, also without PLP, here abbreviated as TR, is the same framework as baseline, but with SLS being replaced by our topology robust extension of SLS. So a single common control law is used to stabilize the system until the consistent set narrowing approach narrows down to a singleton set. So this is indicated as a red bar here. And finally, PLP is the original controller architecture that we've described throughout the slides, with SLS implementing control law design. So here, the predicted mode is used at the beginning of each delta t interval of time until the consistent set narrowing approach converges to a singleton set. So sometimes we get lucky, and our predicted mode matches exactly what the consistent set narrowing approach would have suggested was the true mode. And so we can see the effect of PLP extends across the entire delta t line. So here are the two network systems that we'll be applying the three controller architectures to. We have the hexagon system, which we've kind of seen before, consisting of 7 modes and 8 different modes. It switches according to this transition probability matrix drawn here. The rectangular grid system is a much larger system composed of a 10 by 10 grid of 100 nodes and m equals 20 different modes. Its transition probability matrix is a random matrix with no self-transitions. So recall for the PLP architecture, we needed to design a pattern collection, and here I've added an argument of t to ensure that the pattern collection of interest is a time-varying one to accommodate the fact that the estimate of the current mode is time-varying. For the hexagon system, the pattern collection is described to be the set of all feasible length L mode sequences, and that means that trivially, the pattern occurrence problem reduces to a maximum likelihood problem, and the expected minimum occurrence time is always going to be L, the length of the mode sequence. For the rectangular grid system, the pattern collection is a random subset of feasible mode sequences, because taking a combinatorial sequence of 20 different modes for length L patterns is just not feasible. And so the pattern occurrence problem has to be solved using martingale formulas that I mentioned previously. Okay, so here are the simulation results. We looked at 4 different performance metrics: the LQR cost, error norm, proportion of time the matching control law is used, as well as the runtime. Here's a visualization of states and control versus time, which is relevant for the LQR cost and error norm metrics. The aim for each subsystem I is disturbance rejection, meaning that we want to drive the states x1 and x2 to as close to the 0 line as possible, which is why we observe these kinds of oscillations around the 0 line. At the top subfigure, I also put the visualization of the so true and estimated mode versus time for the baseline and the PLP architectures. And in the bottom, the number of consistent modes versus time for those 2 architectures is also plotted. This is relevant for the prop match metric. Okay, so let's take a closer look at the runtime table. So first, TR simultaneously stabilizes multiple topologies, and so it has a longer runtime than baseline for both of these network systems. Here I've written an X in place of the grid because we couldn't even compute a runtime. We couldn't even finish the code for the topology robust architecture for the grid system. More importantly, baseline and topology robust architectures do not store the SLS control law into memory when they're first learned, and that's why PLP has overall faster runtime than both baseline and topology robust. So this alludes to the first point of the benefits of learning patterns, which is that if we memorize past patterns, we don't have to recompute the repeating control policies. If we look at the prop match table, we'll see that increasing the number of patterns in the pattern collection yields more accurate consistent mode estimates. So recall for the hexagon system, we took the entire combinatorial set of length L mode sequences to be the pattern collection. And for the grid, we just chose a random subset. So compared to the grid, for the hexagon, we're actually looking for a larger number of things. But if we're looking for a larger number of things, then it's more likely that we'll find more things as well. So that's why the proportion of the prop match metric is higher for the hexagon system than the grid system. Also, PLP uses the matching control law more often than baseline. And this can be alluded to the fact that if we go back a few slides, the PLP architecture sometimes predicts the correct mode in advance, or it matches up with what the results of the consistent set narrowing approach is. And so it ends up using the matching control law more often compared to the baseline. So this white part is no longer there for PLP. So this is indicative of the second point. Oops, sorry about that. This is indicative of the second point, where if we predict future patterns, we can also schedule control policies in advance. Okay, so finally, if we look at the LQR cost and error norm metrics, it turns out that the LQR cost for topology robust is the largest, although its error norm is small, and that's because there's more control effort that goes into simultaneous stabilization of multiple A matrices. In contrast, though, the stabilization performance, or the error norm, of PLP is just as good as TR, which is also quite small. So, in conclusion, we've seen that a PLP architecture with consistent set narrowing and consistent set narrowing as mode process ID and SLS as the control law design enables more efficient control with respect to these four performance metrics. Now we'll see if we can demonstrate the same thing with a different application. So that's vehicle traffic network. So in vehicle traffic networks, structural patterns can be exploited. So over space, we might have a rectangular grid where each intersection is a four-way intersection, and there's relatively constant distance between adjacent intersections. Over time, we have some patterns because of human routine. Especially on weekdays, there's heavy traffic from morning and evening commutes. So the PLP architecture for this application will have some major distinctions compared to the dynamic topology network that we've seen before. First, the plant dynamics are no longer a Markovian jump system, but is instead this vehicle traffic network, which will represent as an MDP, a Markov decision process, later in the presentation. We'll also ignore, for simplicity, the mode process ID component, because we'll assume that there are abundant sensors placed throughout the intersection network. And PLP is also replaced with this extension that we call pattern learning with memory and prediction, so PLMP. So you can see, compared to the previous diagram, this PLP compartment is now PL and MP. So PLMP is composed of the following three parts. First, we have pattern learning, in which we identify recurrent snapshots of each intersection. So for example, if there are two 103 vehicles positioned at the north, west, south, and east lanes of an intersection at time 0, then at a future time, little n, this 2103 pattern might show up again. So the key thing that differentiates PLMP and PLP is the implementation of the memory component. Now, there was a little bit of memory in PLP as well, because of the causal nature of prediction, but PLMP implements memory much more explicitly. Namely, we use state-of-the-art techniques in episodic memory and episodic control, especially episodic control, which enhances reinforcement learning techniques by keeping track of state and action pairs and mapping them to rewards, and keeping them in a sort of table, a memory table, for future recall and reuse. Episodic memory and episodic control have been studied in the literature, most notably by Lengyel in 2007, Blundell 2016, and Pritzel 2017. This diagram over here is a form of memory table called a differentiable neural dictionary, which was pulled straight from Pritzel 2017. We're going to be implementing our own version of the memory table for the purpose of this application. And finally, prediction is implemented with the simple one-time step look ahead, because we'll assume, for simplicity, because of these abundant sensors, we can make accurate predictions from the sensor's results. So, for example, let's say at time t, there are no vehicles within the purview of this traffic camera in the center of this intersection, but there are other sensors placed in the adjacent links that say that there's an incoming vehicle from the north and an incoming vehicle from the west. But at time t plus 1, we know that these vehicles are going to enter into the purview of this traffic camera. So this all zeros vector will inevitably become 1, 1, 0, 0. So prediction is basically using this one-time step look ahead, which is based on knowing the constraints of the vehicle traffic flow in this rectangular grid. Okay, and finally, control law design minimizes the level of congestion as quickly as possible. So going back to the previous example, suppose we have 2103, and suppose control law design says that the optimal way to clear out this intersection as fast as possible is to assign green to north-south and then green to east-west. So it becomes 2103 to 2001, and then 0001, and finally all zeros. So let's go into all of that in more detail. We have the network setup, which is an H by L grid network, and each intersection is controlled by one of these 8 light signals. We'll note that there's only light signals for forward and left turning vehicles, and that's because we'll assume right turning vehicles can turn whenever they wish. Congestion control will be solved by posing this problem as an MDP with the following 4 parts. So the state space is partitioned according to nodes, highlighted in dark gray, and links, highlighted in light gray. So a vehicle in the node is positioned right at the stop line of an intersection, and a vehicle in a link is positioned in the road either between 2 adjacent intersections or across an intersection. We use subscript n for nodes and subscript l for links. And the entries of the state vector, so st, n, st, l, just count the number of vehicles that are present in each node or link. Based on this representation of the state space, the patterns are defined as follows. So for this specific intersection H, we define the time-varying pattern collection, so recall this boldface psi notation. So psi sub I of t, which is composed of these patterns for a time-varying number of patterns k of t. Then what we do is we take the nodes part of the state vector and we project them down to only the left and forward components. So that's an 8-dimensional vector because there's 4 directions and 2 different types of turns. The actions, the space of actions is just this space of modes expanded to dimension h times l because there are h times l different intersections in an h by l grid network. And this transition function, t script, abides by the constraints of vehicle movements in the grid. In this simple setup, we assume that each car takes delta ti to cross an intersection, and each car takes delta tl time to cross a link between 2 adjacent intersections. And the more cars that there are in a link, either across an intersection or between 2 adjacent intersections, the longer time each car will take. and it's directly proportional to these delta TL, delta TI quantities. This is to mimic the effective congestion. We'll also assume that there's a maximum number of cars per turn that can cross the intersection per time step and denote that with the variable V star. Finally, the reward function, this R script, is designated by the rate of intersection clearance. So we want to choose the action that will maximize the number of vehicles that depart the intersection per time step. So let's go more into detail about how the memory table is implemented. So the memory table here is mathematically denoted by QCalI. One of the arguments of QCalI takes values from this EQ psi I of t set, which is the set of unique keys of psi I of t. So this unique keys are just a subset of the patterns from the original pattern collection, which represent the entire pattern collection. And each unique key is assigned an equivalence class, which is a subset of the remaining patterns in psi I of t. So we have this kind of disjoint partition of this original pattern collection into its unique keys and equivalence classes. Each entry of the memory table has the following interpretation. So if Qi t psi m is equal to r, that means that as of time t, the best reward of r is obtained by applying mode m to intersection I if its current pattern is psi. So let's go into how these equivalence classes are constructed. First, at time 0, we have our first pattern psi j, and its equivalence class is given by this EQ sub 0 psi j, which is composed of the following two parts. So first, we have every element-wise multiple of psi j up to a factor of v star, which recall was the maximum number of cars per turn that cross the intersection per time step. So for example, if psi j was equal to 1, 0, 0, 0, 0, and v star was equal to 3, then 2, 0, 0, 0, and 3, 0, 0, 0 are all included as part of the equivalence class for psi j. Next, we have every non-zero additive variation of the entries of psi j up to v star. So going back to the previous example, 1, 0, 0, 0, 1, 1, 0, 0, 0, 2, 1, 0, 0, 3, 1, 0, 0, 1, 0, and so on and so forth. Those are all also included in this equivalence class. The iterative update of a new pattern that is observed and its equivalence class is described as follows. So it's empty if this new pattern, psi k, already belongs in the pattern collection either as a unique key or a member of someone's equivalence class, and otherwise it's constructed according to this f function. Now this expression for the f function is kind of complicated, but essentially it just asks, is each psi in EQ0 of psi k, so we construct EQ0 for this new pattern psi k, is each pattern in this EQ0 psi k already in the pattern collection either as a unique key or an equivalence class member. And all of the patterns, all of the entries in EQ0 psi k which have answered no to this question are included in this f function. So the update method of each intersection's memory table then follows similarly to episodic control. So a key difference between the state-of-the-art episodic control methods and this method is just the construction of this equivalence class. So at specific intersection I, suppose psi is the current pattern snapshot observed at time t. Then if psi is not in the pattern collection already, then we just take the k nearest neighbors of entries that are already inside of this memory table. And otherwise, we just fetch whatever was stored in memory. Now these psi hat j's are the k unique keys with the nearest distance to psi at time t, the k nearest neighbors. And here, nearest just means in terms of the L1, minimum L1 NOR between every entry in between two equivalence classes. During training, the Q values of the memory table are updated in the following way. So we compare the existing value with the Bellman update, this R star expression, which should be relatively familiar to those of you who regularly use reinforcement learning. Here we denote bar psi to be the pattern with zeros padded in the right turning positions. And bar psi star is just the next pattern that would occur if you apply mode M to bar psi. This R script sub I is the dimension reduced version of the reward function specific to intersection I. So here's an example memory table for intersection 1, 1 with current pattern 420020 highlighted in blue here. And we'll take V star to be equal to 2 and K equals 3 nearest neighbors. Now the entire memory table is partitioned according to these 8 different light signals, which again, for your recollection, I've put at the top of the orange box. Then the table for mode 1, and the entries of the psi i's, the unique keys of psi i's are indicated by this white circle. So in the subtable corresponding to mode 1, it turns out that this psi is not one of the members already in there. So it has to take the k nearest neighbors, the 3 nearest neighbors, which are all enclosed inside of this red ball. One example of a near neighbor is 120020, for which there's only 3 less vehicles in the east left lane compared to the original pattern psi. In the table for mode 8, there already exists an entry for the original pattern psi, and that's just psi divided by 2. You'll note that the entries are just a division of 2 compared to psi. Okay, so here are the simulation results. On the top left, we have the entire list of the entire list of strategies that we compared against. And in the bottom left, we have the congestion metrics. W represents the average waiting time per car. W sub V is the waiting time, the total waiting time that vehicle V incurred by the end of the simulation duration T sim. And V sub D to T sim just represents the set of vehicles that have successfully reached the end of their routes by time T sim. So the average waiting time per car, the average travel deviation per car D, where dV is the total travel duration of vehicle V, and dV star is the total travel duration for vehicle V under ideal conditions, meaning there's no other vehicles in the network and all green lights. And finally, VC of T is the number of circulating vehicles by time T. So that's the number of vehicles which have not reached their destination by time T. And on the right half of the slide, we have the simulation results. So we'll go over each part of the slide in much more detail, starting with the strategies. First, we have pattern learning with memory, which is a variation of the PLMP architecture with only memory and no prediction. So in this context, this means that if we compare the 2 algorithm pseudocodes, they differ in exactly 3 lines. And PLM bases the next traffic light on the current pattern psi. And PLMP uses the current pattern psi, but it also predicts the next pattern psi star. The variations of our controller architecture, both PLM and PLMP, are compared against these 2 periodic baselines. So we just cycle through these 8 different modes with cycle duration C repeatedly. And here you can see C are multiples of 8, because there is a total of 8 different traffic modes. Okay, so simulation results. First, if we look at the table, we see that W and D consistently increase and decrease in value together for both PLM and PLMP architectures. So if W increases, so does D. This is intuitive because the longer each vehicle is forced to wait, the longer its travel duration increases, so it also increases the travel deviation. We also included exploration, which is common to do for reinforcement learning settings. In the context of this VMDP, we randomly choose a mode from the mode set with some probability epsilon. And it turns out that if we include a non-zero probability of exploration, it ends up doing worse. And this is a trend that we see in both PLM and PLMP. And this is because adding exploration in a structured, predictable traffic setting, like this rectangular grid, leaves very little chance that choosing a random mode will perform better than pure exploitation. Okay, and I think the most interesting result is the plot of VC of t over time. So first, there is a delay until the first vehicle reaches its destination, and this is observed for all four of the strategies that we plotted here, which is a subset, representative subset of the table there. And afterwards, PLMP consistently drops off first, followed by PLM, followed by periodic. So this means that on average, PLMP enables the vehicles to reach their destination the fastest. So in conclusion, we showed that a controller based on learning patterns, whether with only memory or with memory and prediction, allows for improved performance in these three congestion metrics. Broadly speaking, this is similar to the insight we achieved while investigating dynamic topology network application from before. Okay, so in summary, we used discrete time and discrete event jump stochastic systems with repeating jump patterns to demonstrate this controller architecture based on learning patterns. We achieved, so we determined that learning patterns allows for efficient control in two related ways. First, we memorize the past patterns so that we can prevent the recomputation of repeating control policies. And second, we can predict future patterns so that we can schedule future control policies in advance. We confirmed this by looking at a few applications, namely dynamic topology network, for which the patterns were sequences of line failures, consequently topology changes, and the vehicle traffic network, for which the patterns are intersection snapshots. The architecture for PLP and its variations, PLM, PLMP, is shown here, again, for reference, and the publications that were relevant for this part of my thesis are listed at the bottom of the slide. Okay, so now I would like to provide my acknowledgements, and this is a picture of the campus that I took on my first day here in summer of 2017. So many thanks to the wonderful faculty on my thesis committee. I thank my advisors, Professor John Doyle and Professor Sinjo Chung, for their unwavering support and guidance throughout my graduate student years. They have all been available to meet with me consistently, read my work thoroughly, and gave me the freedom to work on various research topics that I was interested in. So I feel very fortunate to be a part of their research labs. I thank my incredible collaborators, Professor Richard Murray and Professor Adam Weirman, for their time and energy to provide valuable feedback and advice. I appreciate Professor Murray and Professor Michelle Efros in particular, for meeting with me regularly these last 4 years. And it was through meeting and having stimulating discussions with them where I feel I've learned the most about collaboration, project management, and more. So thanks to all of them for helping me obtain the necessary skills to tackle research in a rapidly expanding field like control engineering. I also thank my friends, colleagues, and lab mates at Caltech. And it's times like these where I really regret not taking enough photos to include everyone here. But the wonderful memories and conversations that I've shared with you all are things that I will remember forever. And finally, of course, I want to thank my parents for their endless encouragement and support throughout this journey. And with that, thank you so much.
Questions for SooJean from the audience? In the network systems you studied, both of them had no self-transitions. I was wondering what motivated that, or was it just an assumption made for ease of simulation?
I think it was more of a motivation for ease of simulation. So for the delta t, I'm trying to flip back to the slides. For the delta t interval of time, so we also assumed that each mode lasts for a delta t interval of time. So if there are self-transitions, then it might take more than just the delta t amount of time, so there has to be a little bit of nuance in how you treat that, especially for the consistent set narrowing approach, where if you've already narrowed down to a singleton set, but you know that there are self-transitions, when do you know that you should restart the entire consistent set approach, or when should you keep that approach? So I think the version here, we don't necessarily have to have no self-transitions, even for the version of the controller architecture that I implemented here. But I just wanted to provide a little, just in case there were those little nuances I mentioned, that there were for simplicity.
That makes sense. Thank you.
Thanks.
I've got one, I think 47, but I know for sure slide 37. Go to 37. Because about consistent set narrowing, you mentioned that you wait until you get to the singleton before you switch to control. But in like cases here, like by the third node there, you've already ruled out node 1. Do you think it would help PLP or the baseline to like switch to a random one of the consistent sets once you've eliminated what you're already applying control for?
I'm actually glad you mentioned that, because what I mentioned here wasn't entirely accurate, especially for the topology robust and PLP architectures. This is more for the baseline, where we don't have, the best estimate that we have is whatever we had previously. And so we just keep going with that until the consistent set narrowing tells us otherwise. But for topology robust, we actually try to develop a simultaneous stabilization, simultaneously stabilizing control law for the entire consistent set at this point, and then we keep using that until it narrows down to a singleton set, for which afterwards we use the control law for just the singleton. And for PLP, we use whatever predicted node we predicted from beforehand. So what I'm really glad that you pointed that out, because what I mentioned here wasn't quite accurate to topology robust and PLP architectures. So great catch. Yeah.
Thanks, that makes sense.
Okay. Yeah.
Great talk.
Thanks.
Actually going on top of that question, also about the consistent set narrowing. What happens after you find, you narrow down to a singleton, and it's still dynamically evolving topology, right? So then what happens then? You restart because you assume there is no self-transition.
Right. So that's why I had that simplifying assumption where each mode lasts for a delta t amount of time. So it switches at the beginning of the delta t interval, and then it stays constant, and then it switches again at the end of the delta t, and then it just periodically switches like that.
Okay.
So the hope is that the consistent set narrowing approach narrows down to the singleton set within that delta t interval of time, which in this minimal example it does here, like 2, 3, 5, it switched. So delta t I wrote was 10. So at every multiple of 10, it actually switches. So you can see 2 lasts for this entire 10 sequence, and then it switches to 4. So over here, we do restart. Yeah,
okay.
We do restart from the set of possible points.
Okay. And then kind of the second question towards the simultaneous stabilizing controller for the entire everything in consistent set. Did I understand it correctly?
Yeah.
Have you considered a case where that's not always achievable? Like,
Yeah. Yeah, that's a really great question. So theoretically, no. Theoretically, we have not yet considered that. Although, roughly speaking, so the simulations that we demonstrated this for, they worked for those simulations, but there are some conditions in the literature that deal with simultaneous stabilization. I think Blondell in 1992 or 1994 discussed control design across multiple plants for discrete time LTI systems. That was based on the algebraic Riccati equation. And Kao in 1999 also discussed a different set of conditions. So I think that is, there do exist work for theoretically characterizing what those simultaneous stabilizability conditions are. For the general Markovian jump system that we talked about here, that's more of a subject of future work, but yeah.
Thank you.
Thanks.
Other questions? Okay, thank you very much.
Thank you.
And so, are we staying in this room for the committee, or we're going
Yes,
out?
yes, I think we're just.
So everybody